In another video, we gave a formal proof as to y is the quotient set of a set X by an equivalence relation E, a partition of X. In this video, we're going to give a visual proof of the same result. First, let's try to visualize this construction, the construction of forming the set of all equivalence classes of elements X in capital X. Consider an element X in capital X. When another element Y is related to X by the equivalence relation, let's draw a line connecting them. Because an equivalence relation is symmetric, this line doesn't need to have a direction. If X is related to Y, Y will also be related to X, and vice versa. If the relation wasn't symmetric, we would need to give a direction to the line to indicate in which direction does the relationship hold. But in this case, it is symmetric, therefore, we can forget about the direction. Recall that the equivalence class of an element is the set of all the y's in the given set X that are related to X by the equivalence relation. That means that to form an equivalence class of X visually, we would have to collect all possible Y values that are connected with X by a line. This will include X itself, since by reflexivity, every element of capital X must be related to itself. But since this is true universally for all values of X, we can just keep it in our minds that this is so, without a need to draw a line for that. Visually, the equivalence class of an element is such a star-shaped diagram which collects all possible elements of X that are linked with small x by a single line. So, if I form one equivalence class, and then I form another one by the same principle, I will get two star-shaped diagrams. Now let's try to understand how these star-shaped diagrams relate to each other. Is there any overlap? In a partition, we want there to be no overlap. So if X over E is to be a partition, we want these equivalence classes to always be non-overlapping, unless they are the same class. This is because if there is an overlap, that means that there is a single point that belongs to two different elements of the partition, which is not possible because by definition of a partition, every element of capital X must belong to exactly one element of the partition, not two of them, such as in a picture like this. Now, if we ask ourselves, why is it so that the two stars cannot overlap unless they're the same star? Let's investigate what happens if they do overlap, so they have a common element. That would mean that one of the y's from the left side is also one of the y's from the right side. Let's say y3 equals to y6 prime. But this creates a link between x and x prime, making x and x prime themselves related to each other thanks to the principle of transitivity. Every equivalence relation is transitive, therefore, if x is related to y3 and y3 is related to x prime, then x will also be related to x prime. But that means that this x prime itself is one of the y's and the star surrounding x. By transitivity again, the same will be true for all the other elements in the second group, for all the y primes. They are also in the first group because there will be chains of relationships, as you see here, from x to y3, then to x prime, that creates this single relation from x to x prime by transitivity, and then further this relation composed with the other one creates a single one here. And so this is how we can see that in fact all of these y primes belong to the x star. With exactly the same reasoning, but the other way around, by now viewing x prime as the center of the star, we will see that all the y's that surround x are also among the y primes that would surround x prime, because once again there will be direct links from x prime to each of these y's thanks to transitivity. Since there are links of length 3, as I'm showing here, it means by transitivity there is such a link, and then there is such a link, and that will be true for all the other y's as well. So basically, the orbit of this x entirely is contained in the orbit of x prime and the other way around, including the x and the x prime themselves. That does mean that the two stars are actually the same star. They both have exactly same elements. So that is how we can see that these equivalence classes will only overlap each other when they are the same equivalence class. By reflexivity, everything will be contained in one of the equivalence classes, namely its own equivalence class. As we said earlier, x is always related to x. That is the property of reflexivity. So the requirement of a partition that every element is contained in exactly one equivalence class will be met. In fact, visually what this means is that the entire set X needs to decompose into disjoint blocks. And so we have confirmed indeed that these blocks, these stars, will be disjoint. And we also know by reflexivity that everything from capital X will indeed belong to one of these stars. Any random x prime we pick, or x double prime in this case, will have its own star where it will be an element. The other property of a partition, that every element of the partition, in other words, every grouping like this, must be a subset of X, holds trivially, since in these equivalence classes we only pick elements from capital X. We never pick anything outside of the given set. So we have now all properties of a partition that hold. The property that every element of the partition is non-empty holds once again by reflexivity. Each of these will contain at least X. The property that every element of the partition must be a subset of the given set holds as just described. Each of these are indeed subsets of X. And then the property that everything in X will belong to exactly one grouping holds by the argument here about how the two stars would merge if they had any overlap. This is how we can visualize the reason as to why the quotient set X over E is indeed a partition, as soon as E is an equivalence relation on X. As a final remark, note that in each of these blocks, in each of these equivalence classes, in fact, all elements are linked to each other by a line, once again by transitivity. So any two of these objects will always be linked with each other. So visually, these are not quite stars, these are more higher-dimensional tetrahedra, where in the case, if there were just 3 elements in an equivalence relation, we would get a triangle. As soon as there is 4, by linking all of them with each other, we would get what is called a tetrahedron. And now here we'll have a more complex situation where there are more elements in the group, where every 2 are linked by an edge.